Can you see my screen? Shared.
Yes, sir, we can see.
Yep. So, I think this is short courses. Last 2 weeks we are talking about the green ammonia, different way to make a green ammonia and everything related to green ammonia. But I want everyone to sit back and think. Green ammonia requires green hydrogen. All right. Why we need green? Because of the CO2, carbon dioxide, all right? So that means if we start from the green power, which is solar, wind, the hydropower, and then you produce hydrogen, and then there's no carbon involved. The key is we do not want the carbon presence, or we do not want the carbon emission, all right? So once you have that hydrogen, using that hydrogen to make ammonia, that's called green ammonia. So green ammonia requires green hydrogen. Now, we also heard about the blue hydrogen. Okay, blue hydrogen means you have steam reforming, make the hydrogen, and that CO2. If that CO2 is captured and then sequestrated, so the hydrogen here is qualified as a blue hydrogen because there are no CO2 emissions because CO2 has been captured, although the methane is a fossil. Okay, so I think the point is clean hydrogen. The key word here, if you doesn't have the green, the key is clean H2. Oh, sorry. I picked the wrong one. Why? What's going on here? I thought I picked the correct one. Okay, the key word here is the clean hydrogen. Clean hydrogen means there's no CO2. There's no CO2 involved to begin with. Clean hydrogen includes green hydrogen. Okay, so that means when you have the hydrogen produced, there's no carbon present to begin with. Or you start from the fossil, there's carbon involved, but you sequester carbon. So that's called clean hydrogen. Make sense? All right. So let's look at I don't know the production in India. I haven't done the research, the survey in India, but I can tell you the data from US. Today, in the United States, we produce 10 million tons of hydrogen by weight, hydrogen per year, and it's projected it's going to reach 30 million tons. Per year by 2030. I think that timeline has been pushed to 2035. So it's a little bit too aggressive to make to triple the current production, and then by 2030, but at least by 2035, it's going to be 30 million tons. Okay, so now among this 10 million tons of hydrogen, okay, so today among the 10 million tons of hydrogen, how many the million tons for green hydrogen? This is the data. Only 0.12 million. So majority of hydrogen today in US coming from fossil, which is natural gas. Okay. So let me do a quick question. Can you read this question? I just want you to guess.
Yes, sir. We can read it. Can you guess?
Okay. So today, U.S. produces 10 million tons per year hydrogen. How much among this 10 million tons is used for ammonia in the ammonia synthesis? For ammonia synthesis? Just guess. I'm not. You don't have to read it. Just based on your knowledge and your understanding, how much is used. You can pick the guess. Just let's start.
Maybe 90%. 90%.
It's too high. I can tell. Anybody want to pick another one?
60.
Say it again.
60, sir.
60.
Thank you. It's close enough. The answer is 55%. Okay. So very good. Good answer. Very good guess. Okay. So basically more than half has been used ammonia. That's why ammonia is the second largest chemical in US and I think probably around the world. Okay. So the people take advantage of ammonia and then they didn't pay attention to it, but it's the largest chemical. So I mean in day one in my lecture I mentioned without ammonia, well, let me back up. Because of ammonia and then the per acre production of the crops, the rice, wheat, sorghum, anything, it's just because of ammonia or the fertilizer, natural fertilizer, per acre production has gone up. I think the more than 50 years ago. I would say after World War II, and because of ammonia production has been gone up so much, so there's no, I'm talking about average, okay, not in Africa, not in other part of the poor country, just average in the world, the food production or the green production has gone up tremendously, and then people doesn't have to compete with the land. In the old days, World War I, II, everybody want to invade other country, take over the land, and then had resources, and that's not a problem. So that's why I was joking, in day one, without ammonia, probably you will see World War III and World War IV. So because everyone wants to produce the food to feed the citizens. All right. So anyway, so there's a lot of oversupply of the food because of the fertilizer availability. So anyway, 55% went to is going to as the hydrogen go to ammonia, and then most of ammonia are used as a fertilizer. Some ammonia has been used as refrigerant, but still today ammonia has been used as a fertilizer. And then two, because of decarbonization, and ammonia has been used for as other sources. Like in Japan, they combust the coal along together with ammonia because decarbonization. So I think tomorrow is the last day. I'm going to talk about if you have ammonia as a hydrogen carrier, how you turn it back into the hydrogen. I think one day I mentioned to you we use microwave and to decompose ammonia, but there's a different way to utilize ammonia by the ammonia fuel cell. So tomorrow I have a section talk about those. But anyway, so this is the data of ammonia. But I want to make sure everyone understand clean hydrogen is the key. Clean hydrogen means no CO2 emission. So that means you can start from renewable power, do water electrolysis, so there's no carbon at all. Or you can do the blue hydrogen, and then you produce the hydrogen, but make sure and the carbon dioxide is sequestrated. Okay, make sense? So anybody have any question before I begin today's lecture? I want to give you some background information. Anybody have any question? Maybe I can ask you a question for my curiosity. Well, I do have a collaboration with IIT. Now it's the NIT. I also have collaboration with the university called BITS. So I know the professor, but I never asked the question. I'm asking you. Okay. So here's my question. What is hydrogen production per year today in India from what sources? Can anybody tell me what's the US is 10 million ton per year today? I doubt India is more than 10 million tons because the US has a reason they reached 10 million tons. How much is it per year today in India? Anybody tell me, or if you know the data?
Source is majorly coal.
Yeah, source is coal. Yeah, that makes sense because I don't think India has a lot of natural gas. So source is coal. But I think the India produce a lot of ammonia. When I worked for the industry, and then I did a lot of for the I would say the a lot of business in ammonia. It's called ammonia trading. Actually, India is the ammonia exporter, not importer. So that means you must produce a lot of hydrogen from coal, and then to make ammonia. So anybody knows this number, just roughly how much?
It is the second largest producer of hydrogen. India is the second largest producer. Maybe.
Is it more than 10 million ton per year?
Yes, sir. Yes, sure.
Okay, good. So from coal. Yeah, I think because in US from natural gas, apparently hydrogen from natural gas is more expensive than from coal. So that's why if you have a coal to produce hydrogen and then turn out hydrogen into ammonia, so that ammonia is cheaper than from this. Okay, all right, it's good. So good. Yeah, I think it's a very, very good. Yeah, all right. So here's today. If you read the news, U.S. Department of Energy invest $7 billion in clean hydrogen hub. Okay, see the keyword here is not green hydrogen. The keyword here is clean hydrogen. Remember, clean hydrogen include green hydrogen and also include blue hydrogen and also all kind of hydrogen with a zero emission or net zero emission of the carbon dioxide. So that's why U.S. Department invested $7 billion. And then this is the map of United States. You can see their location. So basically, there's 7 hubs. Okay, each hub is $1 billion. See, 1, 2, 3, 4, 5, 6, 7. I am located in here. So we are located, West Virginia University is located in Appalachian Hydrogen Hub. Appalachian Hydrogen Hub and also Gulf Coast Hydrogen Hub, the feedstock to make a clean hydrogen is natural gas and petroleum. Follow me? So in the Pacific Northwest here, since there are a lot of solar and wind, remember when I talk about the renewable power, why we turn the stranded renewable power into the ammonia, because there's so much solar and wind built in this area. And also, of course, California. And this area are renewable power, renewable energy turned into hydrogen, and then you can use hydrogen for ammonia or anything else. And then in this region, which is the Gulf Coast, Appalachian is natural gas. But today, my focus will be on from natural gas. Actually, the shale gas, and also Midwest Hydrogen Hub. Midwest Hydrogen Hub is from the biomass. If you are familiar with the U.S., so in the Midwest, it's agriculture place. There's so much of the storeworks, agriculture residuals. They use that to make hydrogen, and that's another hub. So in the Mid-Atlantic Hydrogen Hub, this is the offshore wind, right? They basically build a lot of wind farm in the ocean, and then they basically generated hydrogen using that. In the California and the Pacific Northwest, those are the solar and wind. They are onshore. That means they are on land. It's not on the coast. But in this particular region, in New York State, Virginia, they build so much wind on the ocean. Any question? Go ahead. Someone asking questions. Yeah.
Sir, compared to the east side, west side has more winds and it is prone to more cyclones and hurricanes. Will it affect the production of energy or anything. Because you are telling that you are moving from west to east. The reason is because of this climatic changes or climatic conditions or any other reasons.
With are you talking about the life cycle? You say the compare some what cycle? Life cycle?
Yes, sir. That is the
Okay.
lifespan of the clean hydrogen.
Yes. Okay. Good. So now you are talking about life cycle analysis. True. Okay. So let's back to here. Yeah. If you talk about the CO2 emission, okay, think about life cycle, green ammonia or the blue hydrogen or blue ammonia. If you based on the life cycle analysis, of course they are different. Okay. So because life cycle, you need to look at basically the a very large range and time scale. So from life cycle analysis, green ammonia is better. But if you look at on your daily life, okay, what do you want? So you basically want, okay, you what on daily life, what do you want? You don't want the carbon emission, all right? So there's another drive in US. I'm writing it down. You wouldn't understand what I'm saying. So basically, this is the goal. By 2035, which is 10 years from today, so US CO2 emission will need to go back to the level of the 2005. So what does it mean? That require the green ammonia, that require blue hydrogen. That means today, your CO2 emission has to drop. Doesn't have to be dropped to zero, so the carbon neutral. As long as you reduce it, go back to the 2005 the level, that's the goal. True, you can continue to go back. Life cycle analysis are different, but if you look at it on the daily basis, yes, you just want to minimize the CO2 emission. You follow me? That's why the clean hydrogen is the goal. So you may say, hey, I want to solve this problem with reach this goal using green ammonia only. But in reality, this is reality. You see what I highlight here? This is reality. There are not enough green hydrogen. So you have to basically have the clean hydrogen. That means no CO2 emission. So to answer the question, life cycle, they are different. Okay. Have you ever heard of let me start another page. Very good question, by the way. So you see, I'm gonna write it down. Okay. Remember, we say so. This is a carbon neutral process. Follow me? You understand what I'm saying now, right? So does everyone, if you use renewable power to generate the green hydrogen and then produce green ammonia, this process is carbon neutral process. Make sense? Do you agree?
Yes, we agree.
Okay. Now my next question. Okay, it's great. So true. The blue hydrogen is not carbon neutral. Blue hydrogen, there's some kind of emission associated if you do the life cycle analysis. Okay. So I'm gonna write down. But it is, but the CO2 life cycle analysis point of view, is much lower.
Yes, sir. Much lower.
All right?
Yes.
Understand that? Then so-called gray hydrogen. Gray hydrogen means you don't capture CO2. You agree, all right? Are we clear about these 2 points?
Yes, sir. Clear.
Okay, now I'm doing since you are asking this question, I'm stretch a little bit. In US, we also drive what is the anybody can give me example? What is considered as carbon neutral, carbon negative process? That means it's not carbon neutral. You actually the negative. You actually sequestrate the carbon in the process. It's called carbon negative process. Anybody knows this and can give me a good example? So green, this is the carbon neutral process. This is not carbon neutral process. What is carbon neutral process? A carbon negative process.
Capturing the carbon from the atmosphere. The process.
Thank you. Very good. So basically, you capture CO2 from and use renewable energy, renewable power, let's say, converted to useful product. Okay? Such as SAF. Anybody know the SAF? Do you want me to interpret it? Can anybody try to say the SAF? What's the SAF stand for?
Sustainable aviation fuel.
It's very popular. I used to read the literature or do something. It's very popular in the world. So basically, it's called the SAF, Sustainable Aviation Fuel. So what is the carbon neutral process? If you capture CO2 from the atmosphere, you're right. That CO2 you captured and then combined with the renewable power, converted to useful products such as SAF. So this is carbon negative process. Thank you. Very good question. Okay. Yeah. You can turn that into ammonia as well, but also the carbon negative because you capture the CO2, but it turns out unfortunately you capture CO2, you will not make ammonia. You have to make the sustainable aviation fuel. Even if sustainable aviation fuel has carbon, but your carbon is from captured carbon. So the whole process is considered carbon negative. Make sense?
Yes, sir.
Okay. Let's continue on. Thank you for the question. That's why I really like this interactive. Keep on asking questions because now I think when I talk about it here, I mean it turns out clean hydrogen, including green, including blue, and then the carbon footprint are different. All right, that's the question, which is good because obviously green hydrogen is carbon neutral, and blue hydrogen is not quite. But if you look at the whole life cycle, only on daily basis you do not emit CO2, but there are some CO2 emission associated if you do the life cycle analysis. Okay, so because of fossil. Anyway, so very good. Then we talk about the different process of carbon neutral or carbon negative. So back to here, the 7 hubs are produced. Each hub is focused on hydrogen production. Okay, so now I'm in the hub of here, Appalachian, which West Virginia. So today I'm going to talk about another color of the hydrogen. Have anybody heard about this the type of hydrogen? It's called let me try. I don't know exactly. Different people pronounce it differently. I heard a lot of time from the British dictionary on the internet. They pronounce it as turquoise, turquoise hydrogen. Okay, Anyway, but regardless, it's the color hydrogen. So what's the color of this hydrogen? It's not green, but it's better than blue, all right? It's something in between, all right? Understand?
Yes, sir.
This is the definition of the turquoise hydrogen. It's a carbon neutral hydrogen. Keep in mind, blue hydrogen is not carbon neutral, okay? Green hydrogen is carbon neutral, but turquoise is a carbon neutral hydrogen fuel that is produced from natural gas through a process called methane pyrolysis. Make sense? It's from the internet. If you do the Google search, you find it. Okay. So now methane pyrolysis. So this is a project. I'm the PI with the partners from the National Lab and the partner from the university and also SoCalGas. SoCalGas stands for the Southern California Gas Company. So all our partners all together. Actually, I'm the principal investigator. So I'm going to present you the process we've been working on, and then which is called the turquoise hydrogen, and then how we produce this carbon neutral hydrogen using natural gas. Okay, so keep in mind, I'm going to refresh your memory. It's a carbon neutral hydrogen fuel produced from natural gas, methane pyrolysis. So here's the process. Methane, you produce hydrogen, but there's no carbon dioxide produced. We produce the solid carbon, which is a carbon nanotube or carbon fibers. So this carbon has nothing to do with the CO2. So if you look at the process, it's purely carbon neutral. And also we drive the reaction using microwave. Microwave is renewable power. We use renewable power, generate microwave to drive the reaction. The entire process does not, even if you start with the carbon, has no CO2 involved. That means it is better than a blue hydrogen. There's no need for CO2 sequestration because carbon in the methane when goes to the high value carbon. Make sense? So you may be wondering, I will come back to this slide. You may be wondering why we are doing this. Okay, this is called clean hydrogen. Why you are doing this? So this is the fact. Okay, the background, the need. This is the map of the the shale gas, the place in US. So this is basically the shale gas in Ohio, and this is actually West Virginia. All this equipment belong to our university because we are drilling, getting shale gas. And then it's the Bakken, North Dakota. And then if you don't convert this gas, you have to flare them. Okay, this is Texas. So that's why when you look at this is the West Virginia, Ohio, this is Bakken, North Dakota, this is Texas. This is the reason United States government invests so much money in here. You see, Texas, West Virginia, and also the Midwest, and then they are all have all kind of the natural gas. That's why the federal government invests the money just try to produce the so-called the gas without emitting CO2. Okay, make sense? So this is the goal. Okay, so let me ask you the question. I'm putting the question, posting questions here. And you understand GHG, right? Greenhouse gas effect. Can everyone read my question?
Methane.
Thank you. Yes. Very few people know because everyone talk about the greenhouse gas, they got used to about the CO2. Actually, no, it's methane. This is the reason you have to flare this the gas. If you don't flare the gas, what's coming out will be methane. okay? And then that's even worse. So you flare, at least you reduce the extent of the greenhouse the gas effect, but still it's very bad. The goal here is we do not want to flare. We want to turn this gas into carbon and hydrogen, and then this is a carbon neutral process. Make sense? Okay. Another question. I'm going to show you a picture. You look at this picture. Where is my? I think I have a picture here. Why it's disappeared? Hold on. All right. So I'm going to go to the internet search. Okay, I found it. I'm going to post my question here. I will come to this question. Oh, read this the picture, okay? This is a picture on the bottom. You heard about shale gas, all right? Does India has a shale gas?
Yes.
You have shale gas. Okay. Can anybody answer me? What is the difference between shale gas and natural gas? Read this. Look at the picture. This is a hint you have.
So for natural gas, CO2 and hydrogen.
Could you repeat the answer again?
Sir,
What is the difference between the shale gas and the natural gas? Anybody has any answer? You said that India has a shale gas.
Sir, as you show in the figure, so it's present in the earth crust area between the natural gas and area.
Okay.
We don't know about shale gas and natural gas really.
Okay. All right. So you don't know. I'm gonna tell you. Okay. Let's do this. Okay. All right. In chemistry, natural gas and shale gas, they are the same. Okay. They are all methane, and then with some other, maybe the ethane and the propane. In chemistry, no differences. Shale gas. What's the differences? So what's the differences between shale gas is the geological formation underground. Okay. So this cartoon really shows you shale gas always is in the shale. Okay. So basically it's the very deep in the shale. And then you are talking about I would say 15,000 feet. 15,000 feet divided by 5, that means 5,000 meters. Go all the way down in the shale. Whereas the natural gas is basically in maybe the 100 meter or maybe just not more than 1,000 meter. Okay, natural gas is close to the ground, and the shale gas is always in the shale. And 100 years ago, people know there's a shale gas in the shale. Just technology will not allow you to drill into the shale. But technology 100 years ago, 200 years ago, even today, only allow you to drill vertically, go into the so-called what you call conventional gas. But shale gas need horizontal drilling. But once you get a shale gas coming out, there's no difference from natural gas. In chemistry, they are the same. just they are in the underground. They are at a different location. Make sense? Here's shale gas, and here I didn't have a full picture. Here's the conventional natural gas.
Do they have any chemical differences, the properties or any other thing?
No, there are no differences. Well, the contaminants are different. For example, natural gas, they may have a lot of sulfur because of formation, but shale gas, because of I think million years ago when they formed in the shale, the sulfur content is very low. But there may be some other contaminants like metals or something. But the majority of the gas, they are methane. Okay, so just they're different. They're different. So so they are in chemistry, they are essentially the same. You're dealing with the same gas, but just when from the production point of view, the shale gas, you see, you drill vertically, you have to drill horizontally, and then you do the fraction to get them out. Okay, make sense? So that's why I have the cartoon, but unfortunately, it's pretty far towards the end. So back to here. All these are the shale gas field. Look at this each individually. They are all shale gas. This is basically the picture shows. If you are familiar with the map of the United States, so I'm seeing from the West Virginia to the Ohio. So basically from west to the east. I mean from the east to the west. Okay, Ohio. And then while we are speaking, there are probably the 10,000 well has been drilled while we are speaking today. And then here is the one of the drilling site by the West Virginia University, because we do a lot of research in the drilling. And here it's called Barken, North Dakota. They're all shale gas. And then basically when you drill shale gas, some gas has to be released because the pipeline capacity will not transport it. So instead of releasing the gas as methane, they have to burn them, flare them, because the greenhouse gas effect on methane is higher. They rather turn into CO2. Another reason they burn it is because of safety. You have to turn the methane into burn them. If you don't burn the gas, and then to release the pressure, and then there will be safety issue. Because there are several issues you have to burn them. But our project is not to burn this gas. We want to turn this gas into hydrogen and then solid carbon. The whole process is the carbon neutral process. Make sense?
Yes, sir.
Okay, cool. So what's the challenge of this? Actually, this is a $3 million project, and it's still ongoing. It's almost 5 years, starting from 2020, right into the pandemic. So, but we started almost 5 years in our laboratory with our partner. It's still going. It will be end the next year. So we have a lot of discovery, which I'm going to show you, and we published a lot of papers. So what I'm presenting to you is already published. Okay. So the goal here is process intensification at a modular scale with objective development flare gas location. Okay. So why the process intensification? Because and the modular. If you look at this, the location, they are so much scattered. You cannot build a centralized plant because it costs so much money to build a big plant and have a gas pipe in the plant. So what we do is the plant, we build a modular and then next to each well. And when the life, the span of each well, and I would say maybe from 2 to 7 years, we move the module like this modular, keep on going. Otherwise, if we build a stationary the plant, which very large, you cannot move it. So the drilling keep on going, and also the production turn this into hydrogen and the carbon nanotube will go along with it. It's called the modular production. It's very popular in today's chemical production. Instead of building a gigantic plant, so-called economy scale, we rather build a smaller. Okay, so that's the reason for that. And then you may be wondering what's the benefit of doing this reaction, so-called what's the benefit of doing this reaction, carbon neutral? here's some benefit. I want to highlight from two economic impact. In a stranded gas location where pipeline is not available, most of the stranded gas area, there are no pipeline. Pipeline always built, in US, pipeline was built 100 years ago. It's already infrastructure already there. But it so happened the shale gas, the location, and shale gas discovery is drilling started 20 years ago. They are not in the many pipeline place. So this is the modular is called distributed production. Distributed production means small scale, decentralized. Then you basically sell the product. Okay. So this is the one of the economic impact that we cannot build the conventional way, but we have to build a distributed. We already talked about environmental impact because if we don't have this the reaction, hydrogen and carbon, you have to deal with the flaring, which is really damage the environment, and then it's not going to good for the economy as well. Okay, all right. So that's the objective. Now back to the business. I think until this point, you should be familiar with the microwave catalysis. All right. So the microwave catalysis, conventional heating, we mentioned is conductive and convective heating. And if you look at the color, external the temperature is hot and inside the temperature is cold. Okay, the heat transfer from outside to inside. And the figure B actually shows the microwave. Microwave heating actually heating from inside out because the microwave only deal with the active site material and then heating from inside out, and that's different mechanism. This is the reason we are using microwave to heat the catalyst and then to drive the reaction. Okay, if you use conventional heating, combustion heating, you are not going to achieve the methane pyrolysis what we need. So, and also this is a cartoon shows the modular unit. When we are successful with this, we are going to build a module. Each module is portable. We can put on the wellhead, and when the production well depleted, that means after 2 to 3 years, there's not too much gas come out. We just move this module, and then from one well to the old gas well to the new production well. Anyway, so this is modular production is very popular. It's more like instead of building a gigantic plant, you build many of those modules and then distribute them together. Then you ship the carbon, and then from each module to the central location, rather than have the central production located. We basically ship the product to the central location. Okay, make sense?
Yes, sir.
Anybody have any question? Anybody have any question?
No.
Okay, so you may be wondering, I keep on showing this experiment. You see the methane plus hydrogen or carbon. This carbon is not amorphous carbon. It's a carbon nanotube or carbon fibers. So this is the reason I'm going to talk about TA at the end of the presentation. So there's a reason we produce the high value carbon. I'm going to show you why. Okay, so okay, I need to balance this. The 2 carbon. There's reason not 2 carbon, 1 carbon. I'm sorry, 2 hydrogen. Okay, so the reason we produce this because this carbon can be made into this. By the way, we don't have to sell the carbon nanotube. This carbon nanotube or the crystalline structure can be made into. I see this product we make. You can sell the carbon nanotube, or can be made into the carbon composite. The key is you have to have a very good, I would say, the crystalline structure to make into this, and also you can build make it into the electrode. Okay, so that's the application of the advanced carbon or the crystalline carbon. But keep in mind this equation. Okay, so before I get into the very detail of the microwave catalysis, I want to ask you a couple quick questions. Let me cut and paste this. So this is what we do. Because methane pyrolysis is carbon neutral. So keep in mind what people do today. So this is basically the before you capture CO2, this is what you are doing. And then I want to ask the question: if you compare with these two, let's put a CO2 on the side. This doesn't. The benefit of this is the environmental. There are no CO2. If you put a CO2 on the side, what's the differences compared with this the so-called steam reforming? I would say advantage of methane pyrolysis. I also want you to say this ad. Okay, so let's start with the advantage. So basically, you can say carbon neutral, all right? And then I would say the crystalline carbon as a byproduct. All right, because you produce hydrogen, you are byproduct.
Yes.
What's the disadvantage? Just look at it. What's the disadvantage? Can anybody tell the disadvantage?
High temperature.
Well, it's not high temperature required. So methane pyrolysis, I can show you the temperature actually is not as high as steam. Steam reforming, you also need 800 degrees C. Okay, so methane pyrolysis, you probably about the same temperature, even more. Yes, okay, all right. Let's see high temperature required. Anything else?
From outside, that's it.
Outside energy? Is that what you're saying? I don't think what do you mean outside energy? So look at the 1 mole carbon stoichiometrically, how many more hydrogen produce? 2, all right? 1 mole in steam reforming, 1 mole of the methane, how many more hydrogen produce?
4.
Make sense?
Yes.
Correct? So basically, poor hydrogen yield because you have lost yield. All right? So you basically, I'm talking about the starting from methane. 1 molecule methane you produce only 2 hydrogen, and 1 molecule of methane you produce 4 hydrogen. Okay, let's put CO2 on the side. So the poor yield of the methane pyrolysis. All right?
Yes.
Okay, very good. So one more question before we move to the next. From economic standpoint of view, you lost the yield, but you need to offset, all right, loss of yield. Just look at equation. How do you want to offset the loss of yield? economically?
Carbon production. Cell carbon.
Right? Because of the steam reforming, yes, you produce 4 hydrogen, you cannot sell CO2. You have to sequester CO2, all right? Now, I produced half of the hydrogen, but by the way, I have the high valence carbon, but I think they together, hydrogen, carbon together, if my carbon, hydrogen together beat your 4 hydrogen, I win the game, all right? You sell the carbon to make the loss. That's called offset. Make sense? All right? Or I would say, or maybe offset or compensate. Compensate probably is better. To compensate the loss of yield, all right? Sell the carbon. But to sell the carbon has to be high value, cannot be carbon black. Carbon black doesn't have any value because that market already saturated. But you have to sell this into the advanced carbon, which is carbon nanotube or the carbon composite. Does it make sense to you?
Yes, sir. Yes, sir.
Okay, so yeah, only when you analyze advantage, disadvantage, you can see the problem. So now my remaining session is all about how you upgrade value. At the end, I will show you economic, how the economic is better than steam reforming, and then all kind of analysis. Okay. Any question before I move on? I'm going to get in deeper how you are going to do this method paralysis.
Can continue with the, like, we don't
Is that question?
We don't have
No question. Okay. All right. So keep in mind this is our product, carbon nanotube. All right. You produce carbon nanotube, but this carbon nanotube doesn't have to be sold as carbon nanotube. They can be sold in a different market. Okay. So now your product is a carbon nanotube. How catalytically you are going to produce carbon nanotube and then sustain the process. So we publish this paper. This may take a little while to interpret to you. I want to stay at a high level. Okay, so how we develop the catalyst using and also the enable the process using microwave. We basically begin with the methane. I feed the methane in the microwave reactor. So this wave represents the microwave. So we have catalyst in the reactor. Methane coming in, hydrogen come out. That's what we want. All right. So hydrogen, methane come in, hydrogen come out. So how do you handle carbon? So carbon will be staying on the what do you call that? On the catalyst. All right. So after that, the solid carbon will be separated using acid wash, and then we separate the product, and then the catalyst is recycled back. Okay, I mean, this is very complex the process. Methane come in, hydrogen come out, and then we have to recover. We have to recover the catalyst because they are so expensive. How do you recover catalyst? Use acid wash, and then you go through the process, and the catalyst coming back, and then the carbon coming out. So the whole process, the key is microwave-driven reaction and also catalyst recovery. Other things is just given. You put a methane into the reactor, or you will see hydrogen. That's very easy. But the key is you are dealing with this solid carbon and a solid catalyst. You have to do the separation, and that's our invention. We invented the process to separate it, and then the pure carbon and the catalyst recycled. Okay, so I can only tell you a high level because if you really have to know why acid wash, why this recycle. But I can tell you it's a black box. Methane come in, hydrogen come out. Then we do the separation, recover catalyst, and then we sell then we have pure carbon nanomaterial coming out. And this cutout really show the reaction mechanism, how microwave interact with the active site, because this process is not the external heating, it's selective heating. Okay, we heat from inside out. Any question until this point? All right. Keep in mind there are two different ways to compare. There's the conventional heating, there's the microwave heating. So you may be wondering, hey, Dr. Hu, so methane pyrolysis, this reaction, I understand. I got it. I know methane can produce carbon nanotube, carbon with hydrogen without releasing carbon. I know this is carbon neutral. So why do you have to use a microwave to dry? Okay, why not conventional heating? Well, conventional heating you have to do combustion. During combustion, you basically release the CO2. But that's not that's only one of the reasons. But key reason is it's the microwave heating is very selective and it's more efficient. And then I think when we talk about advantage, disadvantage, and then I think one of the audience mentioned about the high temperature. Actually, the microwave is not the high temperature. It's If you look at it, it's 550 degrees C. We compare with the conventional heating 600 degrees C, and steam reforming is 800 degrees C or higher. The methane steam reforming. So microwave pyrolysis doesn't have to be very high, operate at high temperature. Okay. So this cartoon really, the data. I know we are close to the break again. So I would like you guys go to break because it may take me a little while to interpret how and why microwave pyrolysis for the hydrogen production and compared to conventional heating, because it may take me maybe a couple minutes to show you the advantage of microwave in driving the methane pyrolysis. Okay, so I think we need to take a break, 30 minutes break, and we will come back. Okay, all right. See you in 30 minutes.
Thank you, sir. Thank you for your session. We'll meet after the breaks.
Okay.